Hello everybody, my name is Misael Cordova and I'm going to present a comparative study of fuel design provisions using AISC, CSA, EC3, JSCE, and AIJ. This comparative study was also developed along with Dr. Mustafa Mohammed, who was my professor at the University of Illinois at Chicago. Introduction. In this comparison study, I'm comparing 5 different specifications from 4 different regions, and this study can be used as a guide for engineers that execute projects in at least one of the areas where these provisions rule. Design basis. In this table, I'm showing that the regulations that we are comparing, they are from 4 different countries or regions, which is the United States of America, Europe, Canada, and Japan. Combinations. The load combinations are defined as the minimum designing loads. And the main loads are the dead loads and live loads. Additional loads are applied only when structures are exposed to external environmental conditions, like wind, earthquake, or snow. The load combinations can be found in the sections that are shown here. Materials. In the United States and Canada, the quality of materials are regulated by the American Society for Testing and Regulation. In Europe, by the Construction Products Regulation, and in Japan, by the International Organization for Standardization, and by the Japanese Industrial Standard. Cross-section. Design specifications have 2 different ways to classify cross-section, which is for the AISC and JSCE, compact, not compact, and standard sections. And for EC3, the C and CSA, we have class 1, 2, 3, and 4. The design members for tension. Members in tension are structural elements that are exposed to axial tensile loads which provoke elongation. In this table, I provide a summary and a comparison of the design equations to calculate the nominal axial strength. For tensile yielding, we have the same equations for the specification study. And for tensile fracture, we have an equation per specification. This is because each specification provides different factors, different reduction factors, to calculate the nominal axial strength. Design members in compression. They are members subject to axial force applied at the centroid of the cross-section. These members can be loaded with an eccentric load. However, the eccentricity must be very small. In this table, I provide a comparison of equations to calculate the compression strength. All the specifications have a similar approach, with the exception of the Eurocode 3, which has 2 different equations for one of the cross sections, class 1, 2, and 3, and a second equation for cross sections with class number 4. Well, all the reduction factors are based on the non-dimensional slenderness factor. In this table, I provide the buckling reduction factor for compression. And as you can see, they have different conditions, and all the conditions are in function of the slenderness factor. Following these equations, you will easily get the buckling reduction factor for different cases. In this picture, we can see the projection of all the buckling reduction factors of all the specifications we studied. The Eurocode 3, the CSA, and the JSCE provide more than one coefficient of imperfection to compute the reduction factor for buckling. This means that they have more than one buckling curve. The AISC and the AIJ compute the reduction factor in function of the slenderness factor, having only one curve each specification. This figure also shows the decline of the reduction factor when the slenderness increases. Thus, the nominal axial strength is affected when the slenderness of the cross-section increases. Design members for flexure. Members can be subjected to bending after applying external load. This behavior could happen on any of its axes. This behavior is limited by two limited states: lateral torsional buckling and yielding. All the specifications provide provisions for the calculations for major and minor axes of different cross-sections. However, this comparison only considers sections on its major axis. This comparison creates a scenario of cross-sections with compact flanges and compact, non-compact, and slender web. The same approach for the specifications with the web is compact for class 1 and class 2. The Eurocode 3, the CSA, and the JSCE utilize the same approach to compute the nominal moment, with the exception of the AISC. Despite of the Eurocode 3, CSA, and JSC have the same approach, the effective area is calculated with different procedures by each specification. The nominal flexural moment were correlated over the plastic moment capacity against the flange slenderness. This analysis demonstrates that when slenderness increases, the normalized flexural moment tends to decrease. However, the reduction is not linear. For slender webs, the nominal flexural moment are close to each value computed by every specification study. A second comparison was performed with several cross-sections with constant flange and flange thickness and variable web depth. In this graph, we can see how the ratio between the nominal flexural moment and the plastic moment decreases when the slenderness of the cross-sections increases. Cross-sections with compact webs, class 1 and 2. This comparison creates any scenario with cross-sections of compact webs and not compact or slender flanges. Same approach for the specifications when the web is compact or class 1 or 2. The Eurocode 3, the CSA, and the JSCE utilize the same approach to compute the nominal flexural moment. The exception with these conditions is the AISC code, which provide different equations. Despite that, the Eurocode 3 and the CSA and the JSCE have the same approach, the effective area is calculated with different procedures. A comparison was performed with compact web and non-compact flange. All the dimensions in this case are variable. The objective of this comparison was to evaluate the change of the normalized flexural moment against the slenderness of the flange. A second comparison was performed with constant flange thickness and web depth and web thickness with variable width. The graph shows a slight decline of the normalized moment capacity when the slenderness increases. For non-compact flanges, the most conservative design provision was the CSA, and for the slender flanges, the AISC is the more conservative than the rest of the specifications. Lateral torsional buckling. Members can be subjected to bending after applying external loads and rotation at one of the ends of the member. All the specifications study analyze the nominal flexural moment when the lateral torsional buckling is applied in compact cross-sections. In this comparison, is only included compact cross-sections. The AISC has a complex procedure to compute the flexural moment resistance based on the embrace length of the member. The AISC has three different conditions and would then also provide the way to compute the nominal flexural moment. The Eurocode 3 and the JSCE They use the reduction factor based on the buckling effect on the cross sections. This is identical to the buckling compression effect. The CSA bases steel design on critical moment and umbrace segments and plastic moment. The AIJ have equations, and these are applied in function of the slenderness ratios. A comparison was evaluated with a W16 by 57 and a HP12 by 84 cross-section, with the buckling length of the beam was variable. It is observed that the most conservative provisions when the slenderness is less than 1 is the AIJ, and when it's greater than 1 is the JSCE provisions. Design members for shear. Bending of steel members generates shear forces in the cross-section. This comparison acknowledges the limited states of shear yielding and shear buckling. The shear yielding is based in the plastic analysis and shear buckling is based in the elastic analysis. Shear yielding. For plastic analysis, the shear is developed in webs on flexural moments exposed to shear forces. The plastic analysis for shear reduces to 58 to 80% of the yield strength. Shear buckling. For elastic analysis, shear is developed in webs susceptible to buckling under shear loading. Normalized shear capacity. A comparison with variable A over H ratio, depth web, and constant flange width, web thickness, and flange thickness was developed. In the shear capacity for plastic analysis, the CSA has a more complex process to compute the ultimate shear strength than the rest of the provisions studied. The Eurocode 3, the JSCE, AIJ, and AISC have a similar approach for this condition. In the analysis performed, the AISC is more conservative. The AISC, the Eurocode 3, and the JSCE have a parallel pattern in every condition. The CSA is the less conservative provision for this case. However, when the ratio A over H increases, the CSA follows the same tendency than the rest of the codes. It is shown that the slope increases when the A over H ratio increases, providing similar results than the rest of the specifications compared. Conclusions. This research provides a brief summary about the structural element design. The results of this comparison pointed the similarities of each specification study. Every limited state analyzed exhibited that every code was based their calculations designed on the same terms. The main difference was the factors applied on every single equation, and sometimes there is a difference of methodology. The analysis performed on this research accomplished with the results expected. When the slenderness of the element study increases, the strength of the element decreases. However, this decrement never is linear. This study also demonstrates the efficiency of elements designed in function of the slenderness of the cross-sections. Thus, slender elements are the less efficient sections for any limited state design. Please send your questions or comments to this email. Thank you for watching.